Good afternoon, everybody, and welcome to this afternoon's webinar. My name is Cheryl, and I'm joined today by Gino Sigismondi, and we have a couple of special guest stars today. We have category Director Matt Engstrom. He is the Category Director for microphones, earphones, and headphones. And we are also joined by Sean Sullivan, who is a Product Manager for earphones and headphones. And they're going to be talking us through understanding earphone technology today. But before we get into that, just a few items of housekeeping. This webinar will be recorded, as they always are. So if you ever want to go back through and listen to this information or point a colleague to it, you can always go to shure.com/training. This webinar will be archived there sometime early next week. There's also all of our past webinars in archive there. So there's a lot of great information across all of our different product lines, wireless, sound reinforcement. There's just a ton of great information there. So please visit shure.com/training for all of your great webinar learning needs. So the other point of housekeeping is, as we go through today, if you have any questions, please feel free to type those in the question pane in the upper right-hand corner of your screen. We will get to questions at the end of the session, so enter them in and be patient. We'll get to as many as we can at the end. If you cannot see that question pane, just look for a little toolbar with an orange box with a white arrow in it, and you click on that, and that will expand it so you can then see the question pane. So that wraps up the housekeeping. I'm going to give it to the experts. Take it away, Gino and company.
All right. Thanks, Cheryl, and thanks everyone to joining us this afternoon here, and Happy New Year to everyone. This is our first webinar of the new year, and there will be many more to come through the following months. I'd like to particularly thank Matt and Sean for joining me here this afternoon. This is my favorite type of webinar to do because I don't have to do much of the talking. I have the experts here to handle this topic for me, although I may pop in with a leading question or two here and there. So this is a topic that is obviously important to us because earphones have been something we've been doing for almost 20 years now, so it's a pretty good long time that we've been involved in this end of the transducer business. Obviously, microphones go back a few years further than that, but they're all transducers. So what we're going to try and cover here today is just a little bit of the history of earphones, like kind of how the whole concept of sticking a loudspeaker in your ear got started, and some of the developments that Shure's been a part of along the way there, but really leading into sort of the meat of the presentation, which is going to be discussing the different types of drivers or transducers that are used in different kinds of earphones. So people often want to ask us a lot about, which earphone should I choose, or what are the differences between the earphones, and really what it comes down to is what kind of driver is in there. And driver is kind of the word that we use to discuss the transducer in an earphone. People often refer to them as speakers or loudspeakers. They're not technically loudspeakers, at least maybe a dynamic could be, but generally driver is a more appropriate word to discuss these. And most of the differences in terms of not only the sound quality, but the physical size and shape of these things comes down to what kind of driver is in there. So we'll talk about the different driver technologies that are used in different kinds of earphones, and then wrap it up with just a brief look at some of the different specifications that are important to earphones, and really earphones and headphones, I guess. But since today we're talking about earphones, and that's based on the fact that it's one of the questions we get probably asked the most. In fact, if you've never visited, we have a pretty extensive knowledge base on the Shure website that it's kind of a frequently asked questions, and that you can actually look at it and see which ones are the most asked questions. And by far, every month after month for I don't even know how long, a couple of years at least now, the number one question is about understanding earphone and headphone specifications. So we thought we'd spend a few minutes kind of tackling that topic a little bit here today. So I'm going to pass it over to Matt, and he's going to start us off with a little history lesson.
All right. Well, thank you, Gino, and thank everyone for tuning in. Sean and I are thrilled to be here again, offering some information that may or may not help anyone. So, Shure began developing wireless in-ear monitor systems in 1995. However, that was not the beginning of in-ear monitors. They had been in the market, made by several manufacturers for several years by that point. And further back, there were quite a few DIY or hand-built units assembled with various wireless technology, perhaps even going back as far as FM radio transmitters and FM radio receivers might have been the first example of a wireless in-ear monitor system. Shure got into wireless microphones in the early 1990s We had been the front end of the wireless portion of a lot of wireless systems, but our involvement ended at the end of the transducer. We realized it was a big area of growth as more and more artists wished to be wireless, and we wanted to keep our microphones atop them, and we figured the best way to do that would be to develop our own wireless systems. So that began quite a long time ago. Within a few years of us beginning to manufacture our own wireless systems, more and more requests for a top quality in-ear monitor system were coming into us. And these were coming from a lot of customers who appreciated what our wireless systems offered, and they had hoped that we could bring a similar level of quality to the in-ear monitor realm. So in 1995, Shure began developing the PSM 600 system. A major part of it now, but not so major back at the time, was the E1 earphone, when we considered a lot of different options in what we might include with the wireless in-ear monitor system. Ultimately, the project team made the very difficult decision to create an earphone from the ground up and to try to educate customers on why that earphone might be better than some of the standard products that were on the market. At that time, the only way you could get a high isolation earphone was to buy a custom earphone, which was at great expense and also not widely available, and perhaps not even the best of build quality available back then because there were so few companies offering it. There were just a small handful of other products that isolated on the market, and none that we really deemed suitable for what our customers wanted to do, which was perform on stage. So that's how the E1 was born, out of a need to create a high isolation, high quality audio experience that was affordable and attainable to not just the very top echelon of customers. So that took a few years to develop. PSM 600 first hit the market in 1997. It was a very successful product. It was very high quality. The audio quality was such that it really distanced the Shure system from a lot of others that were on the market. It really led to a lot of inquiries as far as what else we could do. Could we get more wireless frequencies on the air? And then ultimately a higher fidelity earphone. And in particular, something that provided a lot more low end than what the E1 was capable of. So after some more development, we again announced the first, which was the E5, the first universal dual driver earphone. If you're following along on screen, that would be the earphone on the left on the bottom that Gino was circling with his mouse. That product was clear, so you could see the inner beauty, a dual driver, a dedicated low frequency and high frequency driver. The only way you could get that in 2000, 15 years ago, was with a custom earphone, which required a visit to an audiologist, perhaps multiple refits to get a proper isolation, unlike the E5, which was a $500 product and came with a variety of different sleeve types to offer a hopefully optimized fit. Jumping forward to the next two products mentioned on the page, there are so many things we did in between 2000 and 2013, most notably hiring Sean Sullivan in the year 2005. But a number of other wonderful product launches led us to some wonderful other innovations. The market, meanwhile, has kind of exploded, where we often joke about the parallel between the driver wars in high-end audio and the razor blade wars. How many blades is good? It's got to be better. It's got 5 blades. That's kind of what's going on in high-end audio these days. A lot of assumptions are that the higher the quantity of drivers in a product, the higher output audio quality. And we've never really subscribed to that train of thought. We've designed with different ideas in mind. We've had as minimalist an approach as you can imagine. That might sound odd coming from a guy who directs the category that launched a quad driver earphone. But we do have a really good explanation as to why we did that. So if you stick around long enough in the webinar, you'll hear it. And ultimately, Sean and I and the engineering team behind our most recent launch, the KSE 1500, and how proud we are to be able to sort of reset the playing field, going back to a single driver earphone leading the way for the future. So you said brief. I don't do brief well, but that definitely was history, so I was half correct.
Brief. I'm impressed.
So we'll move into now a little bit on the different types of transducers that are used in these earphones. And Sean, take us away.
Absolutely. Thank you very much. So there are 4 major types of driver configurations for in-ear monitors, or in-ear earphones. The most common being the dynamic driver. A dynamic driver is something that most people are familiar with when they think about a speaker cone in a floor standing speaker and a car speaker. Functions the same way. You've got a magnet with a coil and a diaphragm, and as that current moves through the coil of wire of copper, the magnet moves, pushing the speaker cone, creating vibration, moving air, creating sound. That's probably the most common kind of speaker, and probably the first type of speaker that was used in earphones in general. It has a very natural, warm, comfortable sound without any extra acoustic treatment post-driver. So the sound that comes directly out of that driver is traditionally fairly pleasing to the ear without too much shaping afterwards. It's also probably the type of driver that you find in the most inexpensive earphones. That is the driver also. That's the technology that's in our SE215 driver, our SE215 earphone. And if you've ever heard that, you'll know what I'm talking about by that nice, pleasant sound. A balanced armature is another type of driver or speaker technology that was initially developed for the hearing aid industry. And one of the benefits that you get with an armature driver is the fact that it can be made incredibly small. So this is the type of armature, this type of speaker that you'll find in most multi-driver earphones. Like, these days we've got earphones in the market that have up to 12 drivers in each earphone, in each earpiece. 12 in each side, yeah. It's a little insane, and there are many pitfalls to trying to use a lot of drivers, and we'll get into some of that in a little bit.
But you can't do that with a dynamic driver. I mean, to make it that small to fit multiples in there would be much more difficult.
Exactly. Just the size and the shaping and just the orientation that it needs to fire properly doesn't allow for it to be stacked up with a bunch of other dynamic drivers. Working in the similar magnetic principles, you've got another coil wrapped around an armature suspended between magnets. As that current changes, this reed moves up and down, pushing a pin that drives the diaphragm. You can see the little diagram there on the screen. That moves the air, which creates the sound. Balanced armatures are very sensitive in the high mid-range in general. They are faster, I'd say, than a dynamic driver, in that they can be more accurate, more consistent in general. But they do have a natural peak in that real sensitive range to the ear. So almost every dynamic or every balanced armature earphone that you'll hear has some level of acoustic filtering between the driver and the ear. And that's to shape some of that high energy. If there was no filtering between the driver and the ear, it would be a real shrill sound. It would be very harsh to the ear. Good and bad points to that. Good or bad in the point that you have to control that peak. Good in the fact that it allows for a bit more customization of the sound. So whereas a dynamic driver that we were talking about before presents this automatically comfortable sound without much shaping needed, the balanced armature offers all of this extra energy in that area, which allows you to then shape the energy after the driver to your liking. So you can really customize a balanced armature to sound different more easily than a dynamic driver.
So that increased sensitivity in that mid-high range is what typically allows the balanced armatures to just have a more of a clearer or brighter sound than you get from the dynamics, right?
Exactly. In general, a balanced armature is going to have more of that high-frequency energy, that high mid-frequency energy, which then translates to usually clearer, more precise sounding audio. And like I said, some of them are specialized to be high frequency drivers. You know, they might shine more in the high frequencies than a different balanced armature. And some might be designed really to shine more in the low frequencies. And when we get into those, now you're talking about putting two of them together or more of them together. When you get a dual driver like that, anytime you take two drivers and mix their acoustic outputs, it's you need to be very careful, because where those multiple drivers start crossing over and reproducing the same frequencies in an area, the crossover area, you can get some you can get some cancellation, some comb filtering, some general over accentuation of frequencies, and it just starts to sound very unnatural. And that's one of the things that we avoid when we're making our multi-drivers here. We take a lot of time to make sure that those crossover points are behaving the way they're supposed to be.
And that's what this little circuit board that you can kind of see back here, right, is the passive crossover that's part of the earphone network, right?
Exactly right. And there are some small electronic components that we can fit on there to give us some of the shaping. Particularly on the higher frequency drivers, we can put some small levels of capacitance on the board to help it start up a little later, to get it to prevent it from doubling the lower frequencies of the low frequency driver. There are resistors and things on there so that we can control the amount of energy one driver has compared to the other driver. And once you balance all that out, you can shape what energy is going to the drivers to some point. But like you said, it's passive. It's not like the crossover that you might have in your rack where you can take that electrical signal, process it, and only send a band-limited signal to each driver. That one we don't have. The earphones being so small, there's just no room for active technology in there.
So the end result here then is that, or the reason we would do this with a balanced armature to counteract what you said, them being basically like in a single driver, kind of more emphasis in the mid-high area. Now by putting in a specialized low-frequency driver, you can kind of get best of both worlds, I guess.
So we expand that frequency response to both low and high. I like to think about it as like, one earphone driver might be able to handle a very wide frequency range, but not as much as two specialized drivers that focus on one area or each separate areas of the frequency response. I used to use the analogy of carrying a table. If you had to carry a table from one room to another, you can pick it up and do it yourself, but it's much easier if you've got two people. Did you want to?
When you add more drivers and divide up the work among them, you can also get a little bit more output. So perceived louder volumes is one of the I guess, benefits in loud or pro audio applications, is that each driver can probably get a little bit louder on its own than one could across all frequencies. There would be less natural compression or less suffering at higher volumes. Mm-hmm. Not that we recommend listening very loud, because honestly, we really do not.
And one of the things that people have been striving for had been striving for forever was trying to get that beautiful low frequency to the level that you want it without interfering with the mids and highs. So you want to boost up some of these low frequencies without becoming muddy and getting rid of the clarity. And in one of the earphones that we released a few years ago, the SE846, it's really kind of a one-of-a-kind earphone, and that it is a multi-driver earphone. It has 4 drivers, 2 low-frequency drivers, a mid and a high-frequency driver. And our engineers came up with a way to kind of solve that problem. And that's these low-frequency drivers on their own are fairly flat all the way out to, say, about 2K. And you can see on this graph here, this blue line, kind of represents what those low-frequency drivers, what they would do if they were not treated after the fact. So if you want to get more energy between 20 and 100, you could give that driver more energy. But it's not just going to reproduce that narrow bandwidth that you want. It's going to also start getting in the ways of all your clarity and detail. You're going to boost up everything in the mud range, that 250, 500 range as well. So the low-pass filter that we were able to create, you can see it here in this detail, is these stainless steel plates with that channel cut through it. This is what our engineers came up with, and it's a high inertance pathway. That's what they call it. It's a principle that deals with miniature sound waves or miniature scale audio. Those 10 plates are laser welded together to create one pathway that runs about 4.5 inches long, and it's a very small diameter of a pathway. So the output of those low frequency drivers goes into this low inertance pathway, and all of that energy that it's creating from 2K down to 20 on the way in, on the way out, the only thing that comes out is below, say, 250. And it really acts as a true low-pass filter. It's down about 3 dB by 100 hertz, and it's down 10 dB by 250. And what that allows us to do is to give those low frequency drivers some more energy, and you get this true, beautiful, low frequency, and then it gets out of the way before it starts getting into that mud area or start bleeding into taking out your clarity and detail.
So that's why there's two low frequency drivers in there, is they're both reproducing the same frequency range, but then because of that filter network, we can get rid of the stuff in the mid-range you don't want.
Exactly.
The reason there are two of them is so that we can use a smaller space inside the earphone. I'll refer back to the E5 product a few slides ago. The E5 had a big subwoofer in it. The subwoofer is right up here. That was way bigger than the tweeter. So that's the tweeter. Now, when we fast forward to the SE846, that tweeter is almost the same one found in the E5. Space-wise, it's very, very similar. You can look in the side of the earphones. They're the same. And this is now handling the low-frequency duties. It's a very similar sonic output to what the E5 subwoofer was capable of, although this one has the shaping. Only this one has a much smaller footprint. And that way we have a little bit more space for the mid. So how do you fit 4 drivers inside an earphone? Well, you couple 2 tiny ones together to get a nice round low end, and then going into that low pass filter, we're able to keep a nice low end shape. We even printed the approximate ranges on each driver, so 20 to 200 hertz, 200 to 2K, and then 2K up to 20 kilohertz. Just to show that each driver was very focused in as narrow a manner as we've ever accomplished.
Absolutely. And the beauty of getting those frequencies rolled off as it goes through that filter is once that low frequency driver is there rolled off at 250, the mid frequency driver can take over there at 250 and go up to, like Matt was saying, and they don't interfere with each other at all. I think you actually just said almost exactly that,
Yeah.
but that's the beauty of it.
The last stage in the acoustic network is the nozzle. And whenever you have a multiple driver earphone, no matter what the driver type is, at some point those drivers have to combine. Internally, we refer to it as a little collector tube or a collector nozzle. This is where a lot of problems can occur. Because you're changing the overall size of the acoustic path from the drivers as they go into the nozzle. And when you combine them, we learned the difficult way, this is going to cause a lot of peaks and valleys. So a lot of our time in the acoustic realm is not deciding how things should sound. We can achieve great sound with things that would not look very well in the ear nor fit comfortably, but they sound great. Only when you try to turn that sound quality into something that looks great and fits great in the ear do you enter in things like angles and turns. And if everything could look like a Herman Munster-sized, nozzle coming out of the side of your ear, everything would be great, but it can't. It's got to be low profile and snug. So those the collection area where drivers are combined is very tricky. So for our products, we tend to take a lot of time making certain that what comes out at the end of the nozzle matches up with the target response that we've identified very early. And that's a very tricky thing. And the more drivers you add, the more inefficiencies or artificial peaks and valleys that you add. So we've always been very careful to not overextend our driver stay, if you will, because not only creating the sound, but then manufacturing it and making it small in profile is very difficult.
Absolutely, and the filtering that we were talking about as far as those high mid peaks for balanced armatures the 846 is no different in that those balanced armatures create a lot of energy in that high mid range, and you can see this blue insert here and that goes into that steel removable nozzle. The 846 actually includes 3 different levels of filtering to shape that 1K to 8K kind of speech presence range. To your liking. We have a bright version, which is about 2 dB hotter than the balanced version, which is about 2 dB hotter than the warm version, which we call. And that's all user replaceable. But that's a perfect example of the filters that are required to shape the balanced armature output.
So if I'm following all this correctly, then more drivers isn't necessarily better.
No.
Because you have to be very careful about what you do with them. So in a perfect world, if you could design the perfect earphone, it would be single driver that produces the entire frequency range of interest accurately.
And if it was, the dynamic driver has this mass behind it, and the balanced armature has these moving parts that are required. If only there was like a single massless driver that could be used.
Man, you guys.
That leading question.
Oh man, that was.
I was waiting for the question.
There is no question. Go.
Yeah, the third type of technology that's commonly used in listening products is electrostatic. Electrostatic is revered. Thank you. Revered as being incredibly clear and incredibly high detail accuracy. Companies like Stax and some of the floor standing towers, they've been around for a long time. The electrostatic technology has been around for about 100 years.
If Wikipedia is to be believed. Am I right?
This, however, is the first time, the KSE 1500 electrostatic earphone system, it's the first time that electrostatic has been brought into a sound isolating earphone. So traditionally, electrostatic is over-the-ear headphones, which are large diaphragms that are connected to amplifiers that need to be plugged into the wall, or floor-standing speakers that are powered by high-voltage amplifiers.
Not very portable.
Not portable at all, right? And the almost all of them are open back, which adds to the non-portability of it. They sound amazing, and people love it. I mean, they're incredible sounding products. They're just limited in where you can use them, and
So you just need to be able to sit in a quiet room
exactly
to listen to your music.
exactly, which is
Because
wonderful.
we do that all the time
Yeah,
in
sure.
this day and age.
Nobody's ever on the go.
My car.
But this KSE 1500 brings that electrostatic performance and allows you to take it with you, which is, man, it was a goal that we had. What was it? 8 years ago when we came across the possibility of doing this, and in the last 8 years, we finally feel like we've gotten it to a point where it meets the highest standards of portable audio these days, and really are just incredibly proud to be able to put that performance into the portable audio world.
Well, as we talked about this earlier, all of the transducer types that we've been covering have something in common in that they can both capture sound as a microphone or produce sound as a driver or a speaker. Dynamics are by far the most common, especially in headphones. But we asked the previous audience, so we should ask again if I certainly did this. Has anyone ever used a headphone as a microphone? So there's the raise your hand icon in the.
Raise your hand in the webinar if you ever used a headphone as a microphone.
Yeah, I'm fondly reminded of my Tascam Porta Studio 424 days back in the early 90s and stringing up two of them together and still being out of microphones and remembering that if I half-plugged my headphone in, it would act like a microphone and sticking that in the kick drum and defined my sound as a studio engineer. Just kidding.
We've got about 6 people raising their hands, so.
So the same applies to, believe it or not, ribbon microphones and even condenser microphones. And so we certainly weren't the first company to take a condenser microphone, turn it in reverse. But our engineer had the idea to do it on our sound isolating platform because we had really back then, by probably about 2007, grown our business and really had some success in delivering products that people wanted to buy. And that first hand-built prototype was certainly dangerous and interesting, and it passed audio. We wouldn't say that it sounded great, but by the second version, I'll tell you, Sean and I kind of looked at each other and said, if we could make this, that would be incredible. But back then, a lot of the technology didn't exist. I don't think the marketplace would have been ready, and we really had hopes to put that in our PSM system at the time, thinking that would be the best delivery of audio for our PSM customers. And so that was sort of the beginning of putting our electrostatic system into a portable form factor.
Yeah, in 8 years of development, I mean, we started off, as Matt said, trying to make this and putting it into a stage use. It took a long time to take this large format breadbox amplifier and this really crazy Frankenstein kind of mad scientist looking earphone prototype and make it into something that A, kept that same sound that we fell in love with immediately, and B, was comfortable, durable, looked good, and was portable. And portable, when we started, meant an amplifier that had a line input and an amplified output. As we went through the development stages of this, all of these portable devices now providing digital audio outputs over the last few years. So we said, all right, we're going to include a DAC. We need to include a high-res DAC to build into this device.
DAC is a digital audio converter.
Thank you, Matt. So the amplifier on this device features compatibility, digital compatibility for USB devices such as Mac and PC or Android or iOS devices. So you can take that conversion directly in from your device directly and have the conversion on board in the amplifier. Also has a 4-band parametric equalizer built into it. This was a necessity, as we were talking about the 3 levels of customizability from the 846 that were so popular and so appreciated. I think when you're going to spend a bunch of money on a device that you want to be able to have control over the sound of it to some extent, or to the most extent possible, the popularity of that customizability in the 846 really gave us the nod that we needed to even take that bar and raise it higher with this product. So the KSE 1500 earphone system features a onboard 4-band parametric equalizer that allows you to set frequency, amplitude, and Q value for each of the 4 points. 2 shelves on the ends and 2 peaks in the middle. Really allow you to customize that sound and make it sound like anything you want. And it particularly for the pro audio guys. Go ahead, Matt.
Oh, what I was going to say is, for myself, I'm not a fan of EQing. I rarely do it, and I really love the natural sound of this thing. I fell in love with it. But one thing that has been very clear to Sean and I over the years is that people hear very differently from one another, and they expect and perceive things all to themselves. And this was meant to give that control back and to those who might want it, or to compensate. Mm-hmm. Recordings from all sorts of different generations might have different characteristics, and there has never been such a powerful tool to deliver that as this electrostatic platform. So the EQ combined with it is meant to really compensate for people's variations in hearing or preference and source material over the years.
Absolutely, and the capabilities of electrostatic technology really they can accentuate some points that you don't necessarily want to be accentuated at some point.
Certainly can. The speed is unrivaled of that transducer. And this is a great slide to go to, that correlation one. Oh, unless Gino wanted to make another.
I want to jump back just 1 minute here, because I think you mentioned a great point, which is very similar. It's kind of the earphone version of a condenser microphone. But just for those who may not know what that means, could you explain a little bit about what's going on here in the diaphragm to...
Sure. Like we were talking about before, the dynamic drivers and the balanced armatures and all the moving parts. All of those parts, they take more energy to move. They can't move quite as fast as perfection. Perfection would be something that has zero mass and is just moving air, just sound happening, right? Impossible. The electrostatic driver is as close to that as we can get. We're talking about a small film of mylar, which is essentially weightless, with a conductive coating on it. That mylar is then suspended between 2 conductive stator plates that are creating an electrostatic field between them. And as that electrostatic field, which of course is zero weight, it's literally just air with a charge in it, as that modulates, it moves that almost weightless diaphragm back and forth, creating sound. The moving parts of a dynamic driver, I like to use an analogy of trying to take a bowling ball in your hand and shake it as fast as you can. Now, it's a little difficult because of the weight. Now, when you compare that to, say, a ping pong ball, it's much easier and you can move it much more accurately and quickly. Similarly, the electrostatic driver, being nearly massless, can react so fast. It has an excellent transient response, which equates to incredible accuracy and clarity and detail. It reproduces almost perfectly the source material. And you can see on this correlation graph that Gino just brought up, that first blue peak there is a correlation graph of a section of music, say about 10 seconds of music, that was recorded. That is just the electronic signal, the electrical signal measured against itself. So that blue line there represents perfect correlation. The KSE 1500, that is the measurement of the KSE 1500 reproducing acoustically that electrical signal. And you can see how amazingly close it is to perfection. when compared to this multi-balanced armature driver here, the SE846, which is in its own right an incredible earphone. People have talked about how wonderful this earphone is, and it really is. But
Without
just
bias.
without, yeah, pardon me for being a little biased. Get it?
Yeah.
But that this just goes to show that even no matter how great and accurate that SE846 is, the KSA 1500, that nearly massless diaphragm, really allows it to be even that much closer to perfection.
But then, like a condenser microphone requires power and requires additional electronics, same thing. So that's part of the, I mean, we didn't just come up with an amplifier for this because we thought it would be cool and, hey, let's put this stuff in it. Regardless of all of that, you would have needed this.
Exactly. Any electrostatic transducer is going to require a power source of some kind. It works on, and rather than a traditional driver, which would be more high current, low voltage, this is just the opposite. This is more of a high voltage, an incredible tiny amount of current. But it does require a power pack, like any electrostatic does. And this one happens to be incredibly portable, which is like I said, one of the things that makes it one of a kind.
Okay, so let's move into just a quick overview of some of the important specifications that someone might consider when looking at an earphone, because again, this is a very frequently asked question on our website. What we're going to go over here real quickly is frequency response, sensitivity, and impedance. And let's start with frequency response versus frequency range, which I think is something we always feel a little more comfortable talking about, actually.
Yes, we've always kept the definition of our specification in the frequency range realm. We have not ever published frequency response information. Frequency range, simply, as you state here, two numbers that represent the range of the sounds the device can produce, so from the lowest to the highest, within reason. We don't even specify a plus or minus degree on that. So I usually refer to it in layman's terms as the usable range, the usable audio range, that which you could rely on. If you threw sine waves up at different frequencies, you might find that you would still hear audio in some of our products, but we would say that was out of the usable range, meaning when mixed in with other music, it might not be noticeable. Versus frequency response, which would show you the path. Sean had a great analogy that said you want to get from Boston to California. Well, that's your range, but the response is more the map or how you got there, or whether you went through Canada or Mexico. So you would start and end at the same place, but you would have a completely different looking line of how you got there. And those are very, very difficult. In microphones, we have some nice established standards. Many companies use the same type of test. So when you show a frequency response of a microphone, oftentimes there is decent correlation from manufacturer to manufacturer. This does not exist in headphones or earphones. Instead, we maintain our own testing standards and procedures. A lot of ours are for development and manufacturing purposes. So throughout development, we will watch the certain frequency responses of things as we develop them. And then when we get into manufacturing, we're able to watch that and ensure that our products are manufactured to the same standard. Any deviation is not acceptable. So for us, the testing that we do is often for internal purposes, and that's why we don't publish frequency response information. You might find places that show responses. Some of them might be reliable if you compare a number of products from that same source. Now, if you find multiple places that are doing frequency response graphs and start comparing those, that's when you'll notice some of the differences and anomalies. And really what you find out is that they also have problems in coupling microphones and earphones, or microphones and headphones. And what this causes is more comb filtering or peaks and valleys in the response, and you have these dead zones. So we don't really trust a lot of the response information that gets published from outside companies, but some people have found them useful.
So it is worth noting as well that not only does the measurement techniques from company to company not necessarily match up, but your individual ear canal plays a huge role in what you're hearing. And we can't give you a curve that shows you what the earphone's going to sound like in your head.
Absolutely not, right?
That's what I always tell people is don't get too hung up on this. You can look at the range and get an idea of about how low it goes, and something that can go down to 20 hertz is probably going to have sound like it has more lows than something that only goes down to 100 hertz, obviously. But really, listen to it. Do you like how it sounds? Then don't worry so much about how it looks on paper.
Agreed.
And again, one of the reasons why we don't publish response. What about sensitivity?
Sensitivity. Well, let's see. It's a combination of a lot of different parts that ends up in a mathematical equation saying amplifier output plus specification of driver equals a volume of such. So 3 different examples of earphones. Earphone number 1, 113.5 decibels, sound pressure level per milliwatt. So again, this is a number that is fully dependent on the volume setting and power capability of the device that you're plugging into. So generally, in terms of sensitivity, lower numbers means it's not going to get as loud as something with higher numbers, trying to be as basic as possible in that. So quite honestly, earphone number 2 is 8.5 decibels less loud at 1 kilohertz. All of these specifications are relative to 1 kilohertz, and they will change from lower to higher frequency, lower frequencies to higher frequencies. So that dBSPL per milliwatt rating is not consistent from the lowest low frequencies to the highest high frequencies. Lastly, earphone number 3 is going to be 8.5 decibels higher output at 1 kilohertz relative to earphone number 1. So I'm not sure if I'm answering the question or giving good information here.
I mean,
I'm just sort of speaking about
earphone efficiency
sensitivity.
also in general should be noted that in my experience at least, I've never seen an earphone that was too difficult to drive far past its over loud
A sound isolating earphone.
sound isolating earphone.
Another point here to make, which
point.
it's kind of not to be facetious, but I don't want to say the specifications don't matter, but again, most earphones are somewhere in the range of where they need to be, and louder is not necessarily better. Like, the danger with numbers is sometimes people would look at this and go, well, earphone number 3 must be the best because look at that, look at how much louder it is than the other two. And it's like, well, it is more efficient, and for a given output you will get, signal from your amplifier, you will get more output from the earphone, but that generally doesn't mean that it's better.
Absolutely, and particularly like you said, that's at 1 milliwatt. That's not like a max SPL or anything. Max SPL in these things is way, way above the threshold of pain.
Which is what you see in the area in the red here is kind of the danger zone when you start getting into how long you can listen to earphones at a certain level. So if we look at, say, you put a milliwatt into earphone number 3 and get 120 dBSPL out, that is above the threshold of pain, and OSHA doesn't recommend you be there for any longer than 7 minutes. So,
And that's in a day. That's not in an hour. That's in a day. That's your daily exposure.
daily exposure to that kind of sound pressure level, right? So again, louder is not necessarily better. Could be useful, but then you better be careful.
And so especially useful for in-ear monitors for on-stage use because we can do some non-exact math and say that if we're going to isolate up to 37 decibels, which that's not across all frequencies, so we'll go very conservative and say we're going to isolate 20 decibels. Even though we would hope that the average isolation is that or more. So we're at a rock concert of 115 decibels and we're on stage. So it's probably a little bit louder than in the audience because you're right next to the drummer. So we'll say it's at 120 dB or the threshold of pain. So immediately you're going to isolate 20 decibels by using an isolating earphone if you're using it properly. Now you're up to the 100 decibel level, but you've also got to compensate. You've got to turn up above. So in your ear, it's still 100 decibels if you're isolating 20 decibels. So you would want to turn it up a little bit. And this is basically the same as signal to noise, the noise being the outside sound that you are attenuating by wearing an isolating earphone, and the signal being your transducer on the inside of the ear. So you could still be at an unsafe level even using in-ear monitors because you are trying to rise above the noise level. So just want to make a side
you want
note.
it to be about 6 dB above the noise, right?
That's about where you begin to hear it above that noise threshold.
Right.
Exactly. And so just as a general guideline, simply using in-ear monitors does not mean you are safe. A lot of the materials that are used out there, especially in the custom realm, are hard acrylic. Bang them on a table, they're going to make a very sharp noise, not a very soft thud. A foam or a silicone is going to contour to the ear, and as your jaw moves up and down and your ear shape changes, that earphone isn't going to pop open and let in blasts of sound. So don't assume that because you're using a custom product that you're getting great benefits from isolation. You really, there are ways to get that tested. Certain audiologists have ways of testing how much isolation you're getting. I'll get off my soapbox now, but a lot of people have assumed in the past incorrectly that they're safe simply because they're using in-ears.
Used properly.
Used properly, like anything.
Yeah. And lastly, real quick here, impedance. What should people know about this?
Generally, higher impedance in most products is going to yield a lower sensitivity or a lower overall output potential. Of course, that's not an absolute rule, but that's a general rule. And a lower impedance in general is going to lead to a slightly higher output or a higher sensitivity across a multitude of devices.
And that's partially dependent on the impedance of the device itself, right? So
that factors in, especially with regard to the shape of the sound or the texture of the sound. If there's some impedance mismatching, there might be some sacrifice. For example, a very, very high impedance headphone, something like 600 ohm headphone, plugged straight into a first generation iPod. If anyone ever did that, they would understand that's not a good experience. Very weak output. You're really testing the output power of that old iPod headphone amp. The flip side of that would be very powerful amplifiers of today and super efficient little earphones that once you get that amplifier to setting 1, you're kind of blowing your ears off. And that would be a very high impedance amplifier and a very low impedance earphone.
Mm-hmm.
Yeah, the goal of most of these, the best headphone amplifiers we've seen these days, the lower the output impedance, the better. I mean, a perfect headphone amplifier essentially would have 0 impedance output. That's an impossibility, of course, but the lower you get, the safer you are as far as being able to cover all levels of low to high impedance listening devices.
It's pretty safe to say that with most modern audio equipment, again, most earphones are going to be matched pretty well with that. So as long as you're not using some esoteric piece of strange, arcane gear that might have a very high output impedance on its headphone amp, in general.
Yeah, but they do exist. We get calls.
Sure they do,
it's not uncommon, especially now that we've entered into the realm of very expensive earphones, to say the least.
Right.
Also want to point out that impedance is usually measured and specified at 1 kilohertz. And impedance will change from low to high, especially across driver types. Dynamics tend to be very linear in their impedance across a lot of frequencies. Armatures have a little bit more of a shift to them.
So the thing to watch out for, again, would be that if your output impedance of the device you're connected to is too high or higher than would be expected for this kind of earphone, the earphone just seems to be not as efficient then. It seems too quiet. Right?
Yeah.
And it'll literally change the coloring of the sound. You'll end up getting a boost in some area.
If the impedance gets too close.
Yeah, based on the impedance curve of the earphone itself. Each of these earphones have an impedance curve that it's not flat across. The measurements we see at 1K, if you see an earphone that's like our SE846, for instance, it's stated as 9 ohms at 1K, but it fluctuates from all the way from the lowest frequency to the highest frequency, and its curve is pretty radical. If you're using an amplifier with a higher output impedance, that earphone is going to receive, it's going to reproduce different than what the amplifier will actually change the sound, the tonal characteristics of the music.
If the impedance is too closely matched to that.
Exactly. And that's...
You can't simply match the impedance of our earphone for a high impedance amplifier because you will change the tonal balance of the earphone.
Right. And that's actually, I think, probably the best point to make. And the one thing, microphones, earphones, headphones, whatever, that people commonly misunderstand is they think impedances are supposed to be matched. So if I've got a 16 ohm earphone, then I want an amplifier with 16 ohm output, and the exact opposite of that is true. So that's probably as much as you would need to know about it, really. So don't match impedances. And this is just not really a specification per se, but I think it's always worth talking about because I know we get this question a lot too, which is, are your earphones noise canceling? And no, they're not, but they're sound isolating. And what does that mean?
Technically, active noise canceling, which is what people think of when they say noise canceling, usually found in headphones, and that involves active circuitry. You've got a powered circuit with a microphone that listens to usually a steady noise. It will then invert that, repeat it, and cut that noise out by canceling it out acoustically. However, that will also add some. It will also cancel the frequency of what you're listening to in your music, and it could add some artifacts into the music as well. Whereas sound isolation that we use in our earphones is really just it's not smart technology. It's an earplug, exactly right. We take this very dense, comfortable foam and place it between the source of the music and the outside world, and it blocks out all the ambient noise just by being in the way, absorbing.
Perfect. And no batteries required.
No batteries required.
Great. Okay, so before we get to questions, I just want to mention that this webinar will be archived like all the rest of them are in about a week at shure.com/training. If you'd like to get notifications for future webinars, go to shure.com/subscribe and give us your information, and we will sign you up. So, Cheryl, we got any questions?
We do have a couple of questions. Question number 1. Does Shure offer, or maybe currently in the works, or currently working on a 3D sound system for headphones, as in something that would virtualize room acoustics?
No. As a general rule, if we're working on it, we can't talk about it. I'm most interested in, stereo microphones. We just launched a Lightning microphone called MV88 last year, and so that's a little bit of a different direction than the question that's being asked. So virtual anything hasn't really been a focus for us for our past 90 years, and I don't know that it will be in the future. Yeah.
Yeah, real reality, yeah.
All right. How does the housing affect the sound and the choice of a driver type?
Number of ways. First and foremost, how durable is it going to be? How is the driver going to sit in the housing? The housing material does play somewhat of a role, but between the various resins that we've experimented with and a whole bunch of different things, metals, alloys, and so forth, you can definitely perceive some changes with things like dynamic drivers. With things like the armatures and the electrostatic, I don't believe those changes were as drastic.
Yeah, I agree with you. I'd say that the volume or the space and the shape of the spacing between the driver and the earphone, or between the driver and the rear cavity, is more important than necessarily the material itself. But those little changes in spacing and volumes in between those parts is incredibly important.
Because armatures are closed speakers to begin with, the materials have very little effect, and oftentimes they sit in some sort of mechanism that will help do some shock isolation inside of it, and that's the material that's probably going to have the most direct impact that is not part of the acoustic system. I don't know if that answers the question or not.
All right. Next question. Was there some mention of filters being user changeable?
Yeah. In our SE846 product, you can detach the nozzle, and included with the product are 3 different filter types. What ships on the product is called the balanced filter. Sean and I felt at the time that was the best overall representation, worked across the widest range of genres. Some recordings may be a little bit darker, or people may have a predisposition to hearing a little bit more excitement or brightness. So we have a version of that nozzle that has a little bit less resistance, or passive impedance, if you will. Or impedance anyway. So a resistance cloth is a little bit reduced in a bright version of that nozzle that allows approximately 1.5 decibels between 1 kilohertz and about 8 kilohertz. The bright and the balanced may still be a little bit too revealing on some recordings. As we mentioned, music has been recorded for 100 years now or more, and a variety of techniques have been employed. So for someone who prefers a darker overall sound, we also offer a third variation that has a little bit more resistance in there, a little bit more damping of the high frequency for about a 1.5 decibel reduction from 1K to 8K. So the SE846 is the product that has multiple versions in there.
Great. What do you think about experimentation about possibly combining different driver types?
It's happened. I mean, there are products out there that combine balanced armatures with dynamic drivers, traditionally referred to as hybrid earphones in the market. Not unpopular at all. There are probably 4 or 5 fairly reasonable popularity models out there now that do exactly that. And there's something to it. Just like anything, when you're combining two drivers, you need to be incredibly careful that you make sure that that's done correctly, and you avoid all the pitfalls of multi-driver earphones. And that's you don't get rid of that by changing the two different types.
Yeah, done properly, we've heard some that have sounded very nice. Done poorly, we've heard some that have not sounded nice. Some difficulty matching up the transient responses of a dynamic and an armature. We showed you that correlation curve earlier, and if we were to add a dynamic driver to that list, it would be further to the right than even the SE846. So, yeah, certainly there are some good products on the market, and some good examples and some bad examples.
Great. Well, I think that just about wraps up the time. We haven't gotten through quite all the questions yet, so if you asked a question that we didn't get to, please feel free to email it to us at support@shure.com, and one of our talented and ingenious applications support engineers can help you out with that question. We want to thank you so much for joining us today. We hope you learned a little something, and we will hopefully see you next time.
Thank you.